This meeting is being recorded.
Yeah, the floor is yours.
Thank you.
You're welcome.
Welcome, everyone. Good morning. We are in the third webinar of the NERO Network Cafe, which has the title of Extreme Fire Behavior, Science and Operational Response Needs. Thank you very much for joining us. My name is Nuria Prat, and I'll be moderating the webinar today. Before I introduce the speakers, I would like to give a very short intro about NERO and a few indications about the functioning of this webinar. So many of you already know, NERO is the European Network on Extreme Fire Behavior. It's a cost action that it's providing a number of services to the people who's joining. So NERO gives you access to in-person exchanges and virtual exchanges and conference participations. So within the topic of extreme wildfire behavior, you can participate in those actions. So please visit NERO, where you will find information, and you have the website here, and you can see how you can participate and contribute. The webinar series is organized in the framework of the Workgroup 3, the Capacity Building Framework, that Fabio Silva and myself are co-leading. And we have the objectives that you see in the screen, so change knowledge and experience, improve technical skills, so the researchers understand the needs of practitioners and create and disseminate content on operational tools and foster co-creation. So in this framework, there is this webinar series. This is the third webinar. You can see the previous webinars on the NERO website. They are recorded. This one is also recorded and will also be available on the website later on. So to go directly to the topic of the webinar, today with us we have two speakers. So before, just mention that the webinar is organized as a dialogue between those speakers. First, we'll have an introductory presentation from each of them. Then this will follow through a dialogue or exchange between them both. And finally, we'll have a Q&A with all of you to ask questions and participate in the discussion. So with no further ado, I'll introduce the speakers in the order they will present. So Edwin Cog is the coordinator of the Task Force on Wildfire Management of the Netherlands Fire Service. He's also a representative of the Netherlands in the expert group on forest fires, together with Catalinus II from the Wageningen University. He's a volunteer and semi-professional firefighter within the Netherlands Fire Service. And Edwin is also a coordinator of the National Support Team for Major Incidents of the Netherlands Fire Service and Wildfire Tactical Advisor. Edwin, welcome. The second speaker today will be Professor Domingos Xavier Viegas. Domingos is a full professor at the Mechanical Engineering Department, the University of Coimbra, Portugal. He retired in 2020. And Domingos has been working in the field of forest fires since 1985, mainly in the area of fire behavior and fire safety, receiving numerous awards. He is the director of the Forest Fire Research Center and created the Forest Fire Research Laboratory for the research on fire spread and for firefighter training. He's participated in 80 research projects and contracts supported by national and European funds and coordinated several meetings, international conferences, and courses. He's published over 100 peer-reviewed papers and oriented more than 20 PhD theses in the area of forest fires. He has also been invited by government agencies to report on accidents or large fires in Portugal, Spain, Australia, Croatia, and Israel. So welcome, Professor Viegas. Welcome, Edwin. And please, let's kick off your talks. I stop sharing. So Edwin, if you can proceed.
We'll try. We tried it
Thanks,
before
for the
and then it
presentation.
worked. So let's find out if it will still work. Let's see. Okay. I hope you can see the presentation by now.
Yes, works
No?
perfectly.
Perfect. I can't see anybody of you. So if you have a question or you raise your hand, I can't see it. So please just shout through me and then we can answer the question. That's no problem at all. So first, thanks that I can be here and that I can present about this topic. What's very interesting is that we need to find a way to combine science and the operational needs together to improve firefighting, but also improve risk management, etc. And I hope to give a kind of a view on my statements in this presentation. Thank you for the introduction, Nuria. Like you said, I'm also a voluntary firefighter here at the station where I am right now. So if there's an actual fire call, I have to go, but they are out now. So I hope I don't have to go away during this this webinar. It's a little bit difficult to talk about in the Netherlands. And a terrible to go.
We lost you, Edwin. It's gone, right?
Yes, I think, Edwin, we lost you. We don't see your screen
Hello?
any longer.
Am I gone?
Yes.
Am I gone? No, I
Okay,
stopped
okay.
sharing the screen, but
Yes,
am
we
I
can
back?
hear you now. Yes.
Can you hear me
Yes.
again? I don't know why it isn't working again, so I tried to share it again. Full screen. Okay. It still works?
It's
Yes.
working. Yeah.
Okay. Like I said, it feels a little bit strange to talk about like the Dutch situation or the operational needs, etc., when we have faced a terrible situation in Portugal last week. I was in the happy opportunity to join the Portuguese Special Forces in the National Civil Protection Center a few weeks ago within the NERO project. So that was a great opportunity, and I saw the colleagues working there. And I couldn't imagine which situation would unfold a few weeks later with four firefighters who succumbed in fire and a lot of damage and also other people killed or injured. So I think it's good to have that as the first slide of this presentation, that even if you have a country that is, I think, very prepared for wildfires, I saw the professionalism of all the people over there, you still can face challenges and situations that are too hard to fight, let's say it like that. And I want to use this opportunity to give my sincere condolences to all the people from Portugal and our fellow firefighters within the situation that happened there. And it was a situation, I think it was an example of extreme fire behavior. And some of the pictures I found on the internet of the last week, you can see all the fires that were there at the same time. The red flames are the active fires on the Portuguese Fogos system, the monitoring system. You see some aerial footage of the fires around Porto. You see the smoke, and I found it a very, very interesting picture that the captains of the teams of Porto and another team are wearing firefighter clothes to join and to support the firefighters that fought these fires, and that had a major impact on Portugal. But probably Professor Dominguez is going to say more about that. Okay, then about the Netherlands, the facts. I told a little bit about this in the presentation in Rome too. So compared to Portugal, this is the Netherlands, a very small country, but also with a few wildfire problems. This is one of the pictures Jelmer, he is the National Coordinator Wildfire Management in the Netherlands, made. We are very aware of our risk on floodings and on water in the country, and a little bit less about fire. That is also for us a very interesting point. And with the climate change, etc., this is going to be a much larger problem also within the Netherlands. So last year we made a new vision. We made a long-term plan, let's say like that, to be better prepared for wildfires in the Netherlands. And by now we are seeing with the new government there is a need to cut some budgets, and it looks like that also for the fire service and for wildfire management, the budget is going to be cut. So we can say a lot about how important it is, but if the money is going away, then yeah, we can only just talk about how important it is, and we don't get a chance to do much about it. So that's one of the main problems we are facing right now, to actually make people aware of the risk that also is increasing in the Netherlands. If you talk about extreme wildfire behavior, yeah, I don't want to go too far into terms and into discussions about what is extreme wildfire behavior, but to put it in perspective, you see two types of fires, and the left picture is the fire in the Netherlands in a peat area, which was the largest fire in the Netherlands in the recent past, in the recent 50 to 60 years at least. And you see a fire with a nice, I think, a nice pyrocumulus on the right, which is, of course, from a whole different kind of fire behavior. But in the Netherlands, the left picture is extreme wildfire behavior, because it is too large to fight it with the means we have, with the knowledge we have, with the operational information we have. So I want to talk a little bit more about that in this presentation, and to find a way that I think both fires are, at least for the needs you have in operational way, are comparable. And it's based on what knowledge do you have, what information do you have, etc., to be prepared on how to fight these fires. Still no questions? I can't see anything, so. No? Okay. Yeah, this is a little bit to trigger you all. Is this relevant? We all know this step, I think, with what is extreme fire behavior. Sorry. I hear something. Is there a question?
No, please go ahead.
Okay. We all know this table. I hear something through the presentation, but okay. And like I said, this is to trigger you a little bit. Is this relevant? Is it relevant to know how intense a fire is, or do we need to know what we can do in our own country? And like the previous sheet, I think in the Netherlands, if we have a fire category 2 fire or maybe a 3 fire, we have a lot of issues to extinguish those fires with the capacity we have, with the knowledge we have, etc. And in Spain or Portugal, it will be much less difficult to fight these fires. I've seen it myself when I was joining the Portuguese fire service. So what we need for every fire, I guess, is we need images and videos. What is happening actually during these fires? We need a weather forecast. We need a fire analysis. What is the situation that is unfolding during the day? So what can we predict? What can we expect in fire behavior, etc.? We need information about which vegetation is where, how available is this vegetation, and is all this vegetation fuel, or is it maybe a fire break, etc. And we need to do a real-time fire analysis on what is happening during a fire. And this is where science and operations need each other, because you need to do scientific research to find all the possible ways to know how vegetation is burning, to know what kind of impact the weather can have on a fire, etc. Like we're talking about pyroconvection, etc. We need to do scientific research to know a little bit more about what can happen there, but what is actually happening and how we evaluate that's the next step we need to do together with the practitioners. So if you talk about images and videos, and like I said, I joined Portugal, so I used a few examples of the operational system they are using there to show what you can use. This is one of the pictures that was in the system. So you can see here the fire behavior, you can see the type of vegetation, etc. And you need this information to know which type of fire you have and how you can fight it in an operational way. You need a weather forecast, and on the left you see the Portuguese system. On the right you see the system we are using in the Netherlands when it's dry and there's a wildfire risk. So you need to make a prediction of the weather for the next few days and what is happening and where are the main risks in the country, and what is the risk? Is it a wind-driven fire? Is it a convection-based fire? Is it a topographical fire? We don't have topographical fires in the Netherlands, you can imagine, but in other countries, of course, you have topographical fires. So you can predict a lot of the things that can happen by just having the right weather forecast and using that to make a good strategical analysis of what can happen. And even then, even if you make a good analysis, still the circumstances can be too bad to fight the actual fires. We've seen that in Portugal, because I know their prediction is very, very well. But yeah, if the situation is very bad, then you still have challenges fighting these fires. We need information about vegetation and fuel on the left. Again, one of the Portuguese fuel maps on the right. We also in the Netherlands have our own vegetation map based on wildfire types, on types of wildfire vegetation, let's say it like that. So we have about 25 types of vegetation that can burn during a fire, or that can be used as a fire break by now, like broadleaf trees. In the Netherlands, it's still a fire break. In Southern Europe, it's not anymore a lot of times. And we made a document with the rate spread under different fuel moisture content levels. So we have this kind of information, which is scientific information, but we can use in operational ways. If we know it's very dry and we know the type of vegetation, then we can make a prediction on how fast this fire will spread. And of course, the fire analysis. What is the fire doing? You see the polygons here. You see the spread lines. A little bit more structured on the left on the Portuguese thing than on the Netherlands side, but still you can see how fast the fire has spread. If you can see spot fires, etc. So you need to do analysis during a fire, but also afterwards to understand what has happened during a fire. So, putting science into operation. If we talk about rate of spread, we need information about vegetation and weather information. That's critical to know the rate of spread. So this is the vegetation and weather information is kind of scientific information, but we need to have it in the operational way to know, can we still fight this fire, or is it running away for us? We can calculate fire line intensity if we know which type of vegetation is there, if we know what the weather will do, and if we know the fire line intensity and the type of vegetation, we also know what are our windows of opportunity. We can make a fire typology, and like I said, we don't have topographical fires in the Netherlands, but in kind of all the other countries that are joining here in this webinar, you do have. So if you have information about your landscape and the weather information, etc., and also information about boundary layers, etc., then you can know your fire typology and how to act against these fires. Pyroconvection, very interesting. I saw that there was a question about it previous on this webinar already. Pyroconvection, you only can know if there's pyroconvection if you have good photos or videos, if you know the fire line intensity, if you have the weather information, is the atmosphere capable of producing pyroconvection, for example. So also here a combination of scientific information that can be used in an operational way. And if you talk about operational firefighting versus fire behavior, we have different types of tactics and resources we can deploy. We have hand tools, we have engines, aerial means, those as you all know about it, but you need to know when you can use this kind of tactics and resources. Hand tools you can't use if the flames are 5 or 6 meters high. So you need to find out when you can use which type of resource, and you only can do that if you have information about fire line intensity, type of vegetation, rate of spread, etc. So I think in Southern Europe there are a lot of very good examples where the fire analysts know when a fire starts. They kind of know from the beginning which tactics they can use on which flank, and which flank is the driving factor, etc. And that's something we don't know yet in the Netherlands, and I think we don't know yet in the whole of Northern Europe. But this knowledge that is very, very necessary in operational ways, but it's coming from scientific research. And I think this is relevant for all fires, regardless of their size or intensity. So if you talk about very large extreme wildfire events with pyroconvection, or you're talking about the fire I showed in the Netherlands, which was 700 hectares with a moderate intensity, but for us it was a very high intensity. We need to know this information to know what we are capable of fighting in the fires. And of course, you need to evaluate the fires and you need to validate the models. So you need to improve the models, fire spread models, etc., spread patterns. You need to find out, are our operations, are they still efficient? Are we doing the right things? And of course, are our operations still safe? One of the tactics we always used in the Netherlands was fight the fire from the head. So we just go to the head of the fire and we try to kill the head and then we extinguish the fire. But we've seen with the large fires in 2020 that didn't work anymore, and it was very dangerous because the fire line intensity was too high for our knowledge, for our means we have to fight these fires, and we got some fire engines that had to flee. We had some burned hoses. We had some burned fire trucks in the past in the Netherlands. So we need to know, are our operations still available in some kind of extreme wildfire events or in larger wildfires? We can evaluate efficiency of preventive measures. If you have a fire break somewhere, a fuel break somewhere, did it work like it used to be? Or didn't it work? And why didn't it work in the way that was supposed to be? We need to find out the causes of extreme wildfire behavior. Were there extreme weather conditions, extreme fuel availability, etc.? And I think the situation in Portugal last week, but also the situations in Greece in the like the past years, are very good examples of what was happening there. It were extreme wildfires for sure, but what was the driving factor that these fires are getting that big, and can we do something about it? And we need to know about vegetation. Is the vegetation changing under climate change? Or is the availability of vegetation changing? Like I said, in the Netherlands, broadleaf trees are still used as a fire break. But we see in Southern Europe that broadleaf trees are also burning already, and they are burning on a much higher intensity than pine trees, for example. So if we are using preventive measures in the Netherlands right now, where we use broadleaf trees to make a fuel break, but in 20 or 30 or 40 years, we kind of have the same climate as the southern of France have by now. Is that the right way to make preventive measures? So we need to constantly monitor these situations and evaluate what's happening during the fires. And I think that's a common thing we need to do between operational people and researchers. And if we start a new project, for example, on what is the influence of vegetation on the wildfires, you need to have practitioners and researchers together, scientists together, to find out what is the consequence for the firefighting, for example. And of course, we need to learn from wildfires. We need to have the parameters inside. We need to know which fires happened in which year and what were the conditions, the fire spread patterns, the estimation of extreme wildfire behavior based on previous incidents and research. So if we know already that we have a situation where we have had in the past extreme wildfire behavior, we know that can happen again in if the conditions are the same. So we can prepare our firefighters for a very bad situation, or we can prepare them to be at least to be safe, and hopefully we don't have incidents with firefighters because they are very aware of the situation that can unfold in a certain area. And we need to have dissemination of knowledge for sure within the fire service. So every fire service itself need to learn from the fires that are happening, but also civilians need to know. And that's a very interesting point because, like I said, in the Netherlands, it's all about flood, and we are very aware of the water that is surrounding us, but we are not aware of the fire issues that are within our country and maybe closer to your home than the water issues that's happening. So civilians also need to be prepared on the situations that are going to be much worse in the future, and also the large fires in Southern Europe in the past years have shown that it's not just a thing of the fire service anymore. Everybody needs to be prepared. All organizations involved in wildfire management need to be prepared, but also the civilians themselves need to be prepared. They need to take measures on their own land to prevent fires from getting that big, or at least getting into their houses, etc. And we need to have a dissemination of knowledge between researchers and practitioners. Like I said, I think this is the main topic we need to talk about today. How can we include practitioners in scientific research, and how can we use the scientific research, although sometimes it's too hard to understand for practitioners, to make firefighting safer? I think that would be our main goal, to make it safer, but also to make it more efficient and to make preventive measures more effective. So we need to find out how we disseminate this information, and NERO is one of the great examples of a project that is doing that. And we need to share knowledge between fire-prone and non-fire-prone countries. And then I go to the next sheet, and this is one of my last sheets. That's all about international collaboration. Wildfires, like Mark Castelnou said for a few months ago, fires are not different in Southern Europe than in Northern Europe. A fire is a fire, only the behavior is different, etc. But still, a fire is a fire. And if you know what you can do against a fire, then it's just a natural process. So you need to understand fire to know what you can do against it. And there's a lot of knowledge about fire behavior, about how to fight fires, about what a wildfire can do in Southern Europe. And we need, as Northern European countries, we need to learn from them, from all the experience they have in the past years and all the knowledge they already have on this topic. And it's too easy to say these are different types of vegetation, these are different types of fire behavior, these are different types of climate, so we can't use it. That's not correct. We can use it very well if we translate it into our own circumstances, for example. We need to have exchange of experts. We need to have trainings for people to be more aware of what they can do during a wildfire. And we need to have international aid. Of course, we have the European Civil Protection Mechanism. But in the past year, there were some prepositionings from countries in Northern Europe that went to Southern European countries to be prepositioned there. In two ways, that's a great way of helping. In one way, they can learn a lot from the Southern European countries. In the second way, they can really assist. If it's not during the time they are being deployed and being prepositioned because there are no fires, then it is because they can come next time when there is really a very bad situation unfolding, because they know the system, they know the fire behavior, they know the people. So it's not just about planes, it's about all firefighters. And like we've seen also this year, the issues are getting bigger, and I think in the near future, a lot of countries from Northern Europe will help Southern Europe. And if we have large fires in Northern Europe, we need the help of Southern European colleagues to fight our fires. So in a few years, maybe we have kind of a European wildfire brigade or wildfire service that will assist each other. If the situation in Southern Europe is bad, then the North will go, and the other way around. So it is a warning what's happening now in Southern Europe for Northern European countries. We are going to face, under climate change, more extreme fire behavior. We've seen the fire in Sweden in 2018, in the Netherlands in 2020, in Germany in 2022, in London, in the UK in 2022. There was also a large fire in the Brocken area in Germany this year with a lot of dead wood that was infected by bugs. So you see that the vegetation is changing there, and also the fire behavior is changing there. So we need to prepare. We need to have international assistance, and for sure we need to learn from Southern European countries. So this was my presentation. I directly stopped sharing the screen. So if you need to know anything, this is my mail address, and you can ask questions in the chat for sure. I'll stop sharing my presentation so I can see you again. And I don't know if this is already time to put some questions in of that. Professor Vegas is going to talk first.
Thank you very much, Edwin. Great presentation and overview from Northern Europe and the Netherlands in particular. Appreciate it. If somebody has questions for Edwin for now, please put them in the chat, and later in the Q&A, we'll take them and discuss them. And for now, we give the floor to the second speaker of today, Professor Domingos Viegas. Please, Domingos, if you want to share your screen and go ahead with your presentation. So right now we can see your screen perfectly, but we cannot hear you, Domingos.
Okay, I was mute. Okay, thank you.
Now,
so
perfect.
First of all, good morning to everyone. I would like to greet Teodoro Canals, the head of NERO project, and in his place, the whole NERO team, for having accepted my initiative of giving this webinar. And I'd like also to greet everyone who is attending, and hope that this meeting is useful. I thank also Edwin for his introductory presentation. That was very informative, and I hope that I will be able to also approach some of the questions that he put in his introduction. Well, as you could see from the previous slide, I come from the University of Coimbra. The contents of my lecture will be this: give a brief introduction, speak about modes of extreme fire behavior, and then give some views of the behavior of fires that can become extreme fires. I will revise some basic aspects of simplified behavior based on my research activity in the area since 1985. I must tell you that I was motivated to study forest fires by an accident that occurred in Portugal almost 40 years ago, in which 14 firefighters were killed by the fire. So this addressed very much the issue that Edwin was mentioning. My work is done by a team. These are some of my teammates. They are from different backgrounds, 10 of us. We have PhDs, and we are fully dedicated to forest fire research studies. The methodologies that we employ are these. We do mathematical modeling, we do laboratory experiments, lots of them, field experiments, and also observation of real fires. One of our assets that some of you may know is our fire research laboratory in Lausanne, near Coimbra, in which we have different test rigs, as the ones that you are seeing here: canyon table, a combustion tunnel, the Hadrell table, the wind and slope table, among others. We also have a field where we can perform experiments, and you can see here photos of tests that we did. We do this every year, normally in May, and we are doing this for already many years. And also this is real test, the observation of real fires, because here is where we get the challenge between our knowledge or lack of it and reality, and we get also inspiration to analyze and learn about new problems. As I mentioned, I was very impressed by an accident that occurred in a small town near Armamar, in this canyon that you can see in left side. 15 firefighters were caught by a fire, and only one of them survived. The man that you can see on the right, he is near the place where his son and his brother died in this fire. When I heard about this accident, the news said that there was a change of wind that modified fire behavior and caught firefighters by surprise. This is what is usually reported. And I asked myself what had happened. Some years later, when I visited the site, I saw that it was not a very large place. And if they had time, they could have got out of there. So everything must have happened very quickly and suddenly. And so I decided to know more about this thing that now we call extreme wildfire events. I don't want to go much into the definitions, but as you know, we must distinguish between extreme wildfire events and extreme fire behavior. Extreme fire behavior is associated to the behavior of fire that occurs in extreme wildfire events. And we are talking about extremes, something that is out of normal in the process of fire behavior. In the work that is very much quoted, I am also co-author of this work of the Dean, there is a definition that uses multiple criteria, using the fire intensity, the fire behavior, and also the impact on the population. And in this table, it shows the different criteria. And as you can see about fire behavior, it says that it is unpredictable variations of fire intensity. And also it indicates that the fire intensity is above 10,000 kilowatt per meter. And in this table that was also shown by Edwin, we can see that extreme wildfire events are those that have the fire intensity above 10,000 kilowatt per meter. And you notice that it is said that these fires have what is called chaotic or unpredictable fire spread. This is the question that I want to address. Is it really chaotic? Is it really unpredictable? Or why is it such? Some years ago, I had proposed this definition of extreme fire behavior that is much simpler, let's say, that is only qualitative. And it addresses what Edwin said, because the concept of extreme is relative. For one person, for one situation, a fire can be extreme, and in other situation, it may not be so extreme. As Edwin said about fires in Netherlands or in Portugal. But as you see, I introduced here the two ideas of the technical resources and knowledge. Nowadays, we have some technical resources. We hope that in some years we may have other resources and can be able to suppress fires even of higher intensity. And also the knowledge. This is very important. The person who knows less is less prepared to face the fires, and the given fire can be extreme for her rather than for a person that has more experience and knowledge. So we will talk about extreme fire behavior that occur in extreme wildfire events, and I like to call them manifestations of extreme fire behavior, because that's not a unique form of extreme fire behavior. There are several forms. We have studied some of them, and I mentioned them here. Let me remind you some concepts of fire behavior. Of course, all of us know this, but this is just to have a common language about these concepts and definitions. I'm assuming that you are familiar with all the processes, so I'll not go very much in detail into them, but anyway, if you want, I'll do that. We know that there are different types of fire behavior depending on the layer of the fuel that is burning. Most of our fires, all of them, they have surface fires. We are not dealing with pit fires. And some surface fires can become crown fires, and they can also produce spot. But most of my talk will be about surface fires, but they implicitly include also crown fires and spot fires. Regarding the types of surface fires, we can distinguish between three modes of fire propagation. One is marginal, other is static fire behavior, the other is dynamic fire behavior. The definitions are given in this slide. I'll not waste too much time reading it, but I want to distinguish between static. Static fire behavior is the one that is assumed currently in fire behavior models, because they do not consider the variation of time. They do not consider the interaction between the fire and the boundary conditions. The interaction between the fire and the atmosphere modifies the spread properties and makes the fire dynamic. This is what I'm going to present to you. We can consider different fire behavior properties. I will focus my attention on the main direction of fire spread, let's say the head fire spread. And from it, we will look at the rate of spread of this head. We can consider the average value of the rate of spread. When the fire goes from one point to the other, we can consider the average rate of spread. That is what is usually done, and people assume that the rate of spread is constant during this interval of time. But it is also important to look at the instantaneous rate of spread value. That's the limit of that derivative, and so at given point we have a rate of spread. Another property definition I want to introduce is the basic rate of spread. Basic rate of spread is the rate of spread of the fire in a given fuel in horizontal fuel bed and without wind. So this is a property that is intrinsic of the fuel bed. This depends of different parameters of the fuel bed, but for a given fuel bed, it depends very much on the moisture content. This is an example of the basic rate of spread in a fuel bed of pine needles, Pinus spinacea, of 0.6 kilograms per square meter, varying the moisture content. As you can see, when the moisture content decreases, the rate of spread goes up. So it's very important to know what is the moisture content of a fuel if you want to estimate or predict the rate of spread. I will work very much on the non-dimensional rate of spread. That is the rate of spread divided by the basic rate of spread. This is a non-dimensional number, and it can be used to compare different fuels, different test conditions, and different also situations in the real field and in the laboratory. Actually, the Rotterdam model also uses this formulation, because the Rotterdam model says that rate of spread is a function of the slope of the wind and of the fuel bed properties, and it's given by this equation. Another property that we know that is fire line intensity, I've already used it, that's the product of these three quantities. And these three quantities, the calorific power is practically constant. The full load does not vary much, but what varies quite a lot is the rate of spread. It can vary in 3 orders of magnitude. So it is very important to know the rate of spread if you want to estimate the fire line intensity accurately. And as all of you know, we have different categories of fires depending on the intensity of fire line and the capacity to suppress it with the resources that we have. And nowadays it's considered that the 10,000 kilowatt per meter is the absolute limit for direct attack possibility. You can see here in this graph that for a full load of 1 kilogram per square meter, which is not very much, the rate of spread that is required to have this value, overcome this 10,000 kilowatt per meter, the non-dimensional rate of spread must be about above 20, 30, and so much. And this, we can see that requires quite a special conditions for the rate of spread to be in that order of magnitude. What is affecting the fire spread? We know from the, say, the classical books that we have the triangle of fire factors that are the meteorology, topography, and the vegetation. And I can tell you from now that we have introduced several years ago another concept, that's the concept of square fire factors. We added one side to that triangle, that is the time, the chronological time, because we see that the fire changes, is modified in the course of time, even if the other properties, the other factors remain constant. Let's go briefly to each one of the factors. On topography, we retain usually terrain slope, but it is also important the terrain curvature, because it's not the same thing if the slope is a flat surface or if it is a canyon like here, a concavity, because this modifies quite a lot the behavior of the fire. On vegetation, we can have different parameters. I already highlighted the relevance of the moisture content of the fuel, but I would like to introduce another parameter that is not yet very much studied, that is the residence time of the combustion in the fuel bed. This residence time is very important to assess the inertia of the fuel bed and its dynamic response to the fire. Regarding meteorology, we have different sets of parameters. We have a set of parameters that I call conditioning, because they determine the content of the moisture content of the fuel, and the determining parameters that are the wind velocity and the stability of the atmosphere. So we'll retain the wind velocity as the most important. It is important to make here precision, because one thing is the ambient wind, and the other thing is the local wind at the fire. Local wind at the fire is the sum of the ambient wind plus the wind induced by the fire. And very often people disregard this fire-induced wind. And sometimes it is much superior than the ambient wind, as I'll show. As a summary, we retain the terrain, fuel moisture content, and the wind velocity. These are the main parameters of the modeling. Remember the Rotterdam model that considers these parameters and provides, let's say, results for the rate of spread of a fire in the different sets of conditions. These results from Rotterdam were mostly brought from laboratory experiments like the ones that you are showing here. In these experiments, we can measure the average rate of spread of a fire that is going up a slope or down a slope, and you see that the non-dimensional rate of spread can go up to 6-8 times the horizontal rate of spread. The same with wind. We can have a rate of spread, non-dimensional rate of spread of the order 20, 25, 30 regarding the wind velocity. But what happens is that the fire, if you look at the flames, there are lots of convective processes there, because there are very high temperatures and all that air is moving regardless of the wind. And this movement interacts with the atmosphere. And if you look at the very simple experiments that we can do in the laboratory, for example, in this case, in a slope table with a point ignition in a full bed of pine needles, if you analyze the spread of that fire, we can see here that on the left for 30 degrees slope, the rate of spread changes with the time. And it changes fluctuating, but increasing. For 30 degrees, it's even more, and for 40 degrees, it's even more. You see that the rate of spread is not constant. It is always changing. Of course, people take an average value and say, this is the average value, but with that, they miss all these variations of the rate of spread that are happening during the experiment. And this occurs at all scales that we can imagine. This is even more evident if you look at the fire in the canyon. This is a test table that used in our preliminary work. And on the right, you can see different repetitions of the rates of spread of the head fire for 20 degrees inclination of the middle line of the canyon, and below a 30-degree inclination. You can see in the figure below, the fire spreads suddenly goes to very high values of 35 non-dimensional value, and then it decreases. This is why we added this fourth side to the triangle. Let's now look at some manifestations of extreme fire behavior. I refer to two of them. One is what we call eruptive fires in canyons, and the other are the junction fires. What are eruptive processes for us? This is on the left a volcano, and on the right is a fire. And again, we see that table, and I'll try to show you this video. It's in the laboratory. It's a 3 by 3 meter table. And as you can see, there is no wind. The full bed is homogeneous of pine needles. We put a small fire there. And initially, it's a small fire. Firefighters they think they can extinguish it with their boots, and that's true. But if you see, given the shape of the terrain, air is being entrained by the fire and is feeding the head fire, and the head fire is being modified. The flames are getting bigger and bigger. This means that they are spreading faster. And if firefighters are not able to catch them very soon, they are maybe caught by this. And if they try to run ahead of this fire, they will lose this race. Sometimes firefighters come to the top of the canyon with the fire truck, and they think they can wait for the fires and suppress them when they reach at the top. But as you see, they can be caught by this. If you look at this image, what is changing in this fire behavior is time, because all the three other factors are constant. It's the fire-induced convection that is modifying its behavior. So this is the process that brought our attention to this problem, because we realized that many accidents with multiple fatalities occur in this type of terrain. You can see these are snapshots of the same experiment at different times. And this is very different from the initial ignition from what we see there. That fire that you saw at the end is the same as you can see here, the same type of work. Well, what happened here is that the presence of the fire, if there is a flame with a certain rate of spread, with a certain ambient wind, the presence of the fire will modify its surrounding. It will increase the wind velocity. The wind velocity increase will bring more oxygen to the flame and will increase the flame height and the rate of spread. And this is a process that has a feedback. So higher rate of spread, more wind will come and more increase of the flames. So this process prompted us to derive a mathematical model to explain this. if we assume that the rate of spread depends on the wind velocity, local wind velocity as that function, deriving that function, we have this equation. And then we have to assume that if there is the flame there, it will modify the local wind of local wind in the course of time by this function. And combining these three equations, we can suppress the dependence on the velocity and derive this differential equation. This differential equation explains the rate of spread variation in time due to the properties of the full bed. And as you can see, this derivative is only equal to 0 when the non-dimensional rate of spread is equal to 1. This is only on a horizontal full bed, and without wind, the rate of spread will not be modified. We'll have a constant rate of spread. In all other cases, we'll have a change, a variation of the rate of spread. You see that I introduce here the reference velocity and the reference time, the residence time of the full bed. That differential equation can be integrated numerically, and the solution is given here as this straight line. And here is the comparison between the model and the observed values in 5 experiments in canyons at the laboratory scale. This curve depends on the full bed. If you have the same test but with a finer full bed like straw here, you see that the processes are much faster. Here you see an experiment that we did some years ago in the field with a large-scale canyon. It has around 200 meters scale length. And the same process occurred. At the beginning, fire spread very slowly, but after 20 minutes, it erupted and burned all the canyon in a very few minutes. Using the parameters of the model, we can provide solutions for different fuel types. This line is for straw, this is for pine for liter, and this is for shrubs. This curve is the most interesting for operational applications. It shows that after 10, 20, 30 minutes, the fire will go up. The rate of spread will increase rapidly. The problem is that when firefighters go to a fire, they don't know exactly where they are, if they are at this time or this or that. The point of start depends on the boundary conditions of the fire. And many accidents have occurred that we have studied in this frame of time of 20, 30 minutes. I now mention a second type of extreme fire behavior that is caused by junction fires. This comes from the merging of two fires. My attention to this was brought first when I was called by the government of Australia to analyze these two large fires that occurred in 2003 near Canberra. And I was informed that between the two fires, these two fires, there appeared a third one, as you can see these time frames here, and this third fire spread very fast in the direction of Canberra and caused a lot of damage. And I was asked, what was this third fire? And I didn't know. So when I came back to, well, this fire caused different convective processes like tornadoes, that I mentioned soon. I came to the laboratory and we created this experiment that is two lines that merge together. And what we observe is that when they are ignited, they burn very quickly and they create in between them a fire that spreads very fast. You can see this in this video on the left with infrared camera and on the right with video cameras. You see, normally this is a 6-meter table and it will take about 5 to 6 minutes to burn. But with this type of ignition, it burns in less than 1 minute. This is something that is not predicted by Rothermel model, because if you apply the Rothermel model to each point of those ignition lines, it would give the same rate of spread, but that is not at all the case. So there are convective processes that are generated here by the fire that modify the the behavior of the fire. And what happens in this case is that the non-dimensional rate of spread of the head fire can be as high as 100, 160, and even more that we have seen in some experiments. For example, for 40 degrees slope, the non-dimensional rate of spread can reach 250. That is much higher than what we have in let's say, wind effect only fires. We did also field experiments with different scales. And you can see here a sequence of infrared images from one of the plots. You can see after 70 seconds, so 1 minute and 10 seconds, the whole plot is burned. This again would take normally around 15 to 20 minutes to burn such a plot. You see that also very important convective processes are created, fire whirls, and in the center of the fire there is a sort of tornado that is formed, induced by the fire. These are results from this type of fires at different scales, the laboratory, field, and also the camera fire rate of spread. You can see the values there. Okay, more recently, we've been proposing a concept of what we call intermittent or oscillatory fire behavior. This occurs because if you have a flame here, flame front, with a certain wind, the wind will incline the flame and the fire will start to spread faster. And this process will go and go because, as I said, the flame will be fed and it will increase, and the process of spread will be, the rate of spread will go increasing like this in the course of time. But when this inclination is very pronounced, there will be a contrary wind on the other side, and this wind will tend to stop this fire and to put the flame again vertical, and the rate of spread will decrease. And then we'll start a new cycle like there and start a new process. So the fire spread goes up, then decreases suddenly, then goes up and down. This is what we call intermittent or oscillatory fire behavior. We proposed this concept in a paper a couple of years ago, and you have studied it extensively. We observed that this occurs at all scales of observation. On the left, you can see a laboratory test, in the middle, a field experiment, and on the right, real fire. You see we use always seconds for the time scale and the centimeters per second for the rate of spread. But you can see the values of the scales vary quite a lot, because the size of the experiments is much different in one case than that. But the process is the same at all scales, and this is also observed in these experiments here. We analyzed the oscillatory variation of the rate of spread in all these scales and measured the amplitude of this variation. And we found that this amplitude of variation of the rate of spread varies linearly with the rate of spread. You can see here the rate of spread in our observations is changing 4 orders of magnitude, and this linear behavior is found. Of course, it's not the same line. For example, here the red dots are for large fires, these are for field experiments, and these are for laboratory experiments. For laboratory experiments, the oscillations are small, but for large fires, the oscillations are very large and with a large amplitude. This explains why we cannot get from laboratory experiments, we cannot predict what is happening in large fires. Patron-Mel model was built from laboratory experiments. So we cannot expect that we are getting there all the variability that is observed in real fires. So this is some word of caution that we must make about the Patron-Mel model. Let's skip this. Patron-Mel model in 1991 published a paper where he tried to predict the rate of spread from very large fires, including crown fires, using his model for surface fires. And he found that the model underpredicted the rate of spread. He found that it would be necessary to multiply the values of the model by 3 times to get the average rate of spread of large fires. So this indicates the error that we can make here. And besides, if you are looking at the average value of the rate of spread, you can be missing the fact that that fire can reach maximum values that can be 3 or 4 times the average value. So this is very, very relevant for prediction of the rate of spread, especially if you are considering the safety conditions, because one thing is the average rate of spread and the other is instantaneous, that can be much higher, and the rate of spread can vary quickly, suddenly. I already showed this type of plots. It's observed quite often that the rate of spread goes to very high values, so the fire accelerates, but then it decelerates. And I've had several reports on fires when this happened, namely the report on this fire here. And the authors have great difficulty in explaining this decrease of the rate of spread, this deceleration. The increase can be more or less invoked even using the 3 factors. Of course, topography cannot change. They use the fuel, or they use the wind. They assume change of the wind. But for example, for the deceleration, it's not easy to explain. And there are many disparate explanations that in the same paper that do not justify what happened. I bring here an example of a fire in Portugal in 2017 in Lausanne. This was perhaps the major fire that we had in Portugal till now. And it started at a given point here by an electrical line, and it spread in several hours. And we analyzed this. This is a construction of the fire from field work and also other material, other data. And you can see the rate of spread goes up and then increases very much, and then it comes down. This in the course of time. If you look at the wind velocity in this period of time, it's shown here. Of course, it varies, but it does not explain this acceleration. So this is something that occurred due to the convection created by the fire itself, and this is what we observe in different situations. This is a series of images that I got from the Israeli police from a fire that occurred near Haifa. And you can see here all these points, as they accelerate, they create this vertical puff. If this is a large fire, this can become a pyrocumulus whatsoever, as we observe in large fire. So we now come to this problem of fire acceleration and deceleration that I mentioned, that you observe. What we see is that the analytical model that we proposed, the differential equation that we proposed to explain the acceleration of the fire, the same equation can be used to explain the deceleration phase. Of course, with different parameters. This is negative and explains the deceleration. And physically, what happens is that when this fire is accelerating, it is increasing, but then there is a wind that comes from the other side that stops the fire and reduces the effective wind here near the combustion zone and decreases the rate of spread very fast. We developed, integrating those equations, we developed these curves using a set of parameters that fits most of situations. It's not, let's say, there are, of course, conditions that do not fit exactly these curves, but we get an explanation for both the acceleration and deceleration of the fires. And this result can be used to, for example, estimate the time it will take the fire to accelerate from a given rate of spread to another one. And using these curves, we can determine the time delays that will take to accelerate the fire from one point to another. This is important because in operations, if the fire is spreading at this rate of spread, and if we know that it is accelerating, it's important to know after how much time it will reach the peak, and when, because we can also integrate the rate of spread and estimate the distance. Or if we know that it is decelerating, how much time it will take to decelerate and how much time it will remain there. Because this is an opportunity to deploy forces and attack the fire when it is it has a lower rate of spread, or eventually to evacuate people that may be in danger ahead of the fire. These are comparisons between the model and the observations from a series of real fires that we analyzed. With this, we are now about to publish a paper on this. We are exploring these results. We are looking for more data on fire. To conclude, I don't know how with time, Nuria?
Yes, please go ahead, and yeah, these examples will be
Okay.
closed.
5 minutes. 5 minutes. Okay. I'll give just 2 examples to illustrate what I showed. First one is about the eruptive fire, and the other is about the junction fire. About eruptive fire, I described this accident that occurred in 2003, in which there were 2 victims. The fire occurred in this slope, and the wind was blowing down slope, and the fire happened here in the bottom near the river. The firefighters, the fire was contained around here, but they could not suppress it before it entered this canyon. And when it entered this canyon, it erupted in the canyon and burned the whole slope in less than 20 minutes and killed 2 persons that were there. When I went there, I saw that there was a meteo station on the top of the ridge. You can see here on the top of the ridge, there was a meteo station. And the meteo station data showed this. At the time of the accident, these are 10-minute average. The temperature went from 30 degrees to 52 degrees. The wind that was blowing downslope turned 180 degrees and started to blow upslope. And the wind velocity average that was of the order of 10 kilometers per hour went up to 62 kilometers per hour in the time of 20-30 minutes. The gusts went up to 92 kilometers per hour. Of course, this was caused by the fire eruption, and you can see what was the power of the fire to modify the surrounding environment. The Pedrógão Grande fire is one that you know quite well. We have studied it extensively. We established that it was started at 2 points on an electrical line. At this point, at around 2:30, and at another point, 3 kilometers apart, 1 hour later. And this created 2 fires, as you can see here. This more developed and that one less developed. This one was already quite difficult to suppress. The other one was left unattended. But there was a thunderstorm that was approaching this area, and this thunderstorm created a downburst, and it modified the behavior of these 2 fires. It pressed them towards the ground, and they started to spread parallel to each other. And from video cameras, we have this full history of the fires. You can see on the previous images the fire spreading from right to left towards the sea. But when the 2 fires start to join, they merge, and as you can see, they merge as a single fire. And at this time, at 20 hours, between this time and 21 hours, the 66 fatalities occurred in this area. So you can imagine a circle of 10 kilometers diameter, hundreds of people there trying to get out and always feeding themselves in the middle of the fire. So you can see here one's fire and the other, and they started to spread and they merged and they created a very fast rate of spread. We created physical simulation in the lab that I'm going to show you. These are the positions of the fire at this time, 7:30, when they started to merge. Now, this is in the wind tunnel, we put the wind. On the figure, you can see the main roads, and each green dot is a place where an accident occurred. Here, in this stretch of 200 meters of the road, there were 30 people killed in this place. You can see the fires merged and created this. We made experiments with a single ignition, and the behavior was completely different. It's the fact that there were 2 of such ignitions that caused this effect. The consequences are these that you know well. In some places, we had wind whirls, wind tornadoes. We calculated the wind velocity required to break these trees was of the order of 200 kilometers per hour. So this is again a wind induced by the fire. And the fatalities at this place that I mentioned. We analyzed this very carefully, and the rate of spread of the fire, of the head fire, you can see in the as this green line, this is acceleration, and this is the deceleration. And these are the results of different laboratory experiments that we did. Again, we have this process of acceleration, deceleration. The rate of spread in this fire reached around 12 kilometers per hour, 12, 13 kilometers per hour. If you allow me, let me finish with the simulation of the accident that I mentioned at the beginning of the Armamar. The firefighters were killed inside this canyon. They were on the top of the canyon. They were entered the canyon to go across the valley, but they did not realize that there was a fire in the valley. You see, there is wind in this direction. When they reached the bottom of the canyon, they noticed the presence of the fire, but you see what happened when the fire reaches the canyon. So from the 15 men that were there, only one survived because he was lucky enough to be behind this wall of stones and got himself protected. All of them died. There's a very similar situation occurred in 2013 in Yarnell, where 18 firefighters were caught by a very similar situation. They were coming down this canyon, they were here, they even deployed their fire shelters because they were caught by a fire that was coming in the bottom. So you see, these are examples of things that happen in fires. And when you have this extreme fire behavior, things can happen very quickly, very suddenly, because the wind induced by the fire modifies completely the fire spread. To conclude, I say that sudden fire behavior is essential to understand all processes associated to wildfires. Behavior of fire is dynamic, and the interaction between the hot gases and the fire cause this in the environment. Recent studies of our team show that fire behavior is oscillatory, which induces a prediction error that is proportional to the average rate of spread. So there are intrinsic errors in the fire prediction models. Then sometimes the fire may assume conditions of extreme fire behavior. So these oscillations can reach a very large amplitude and very large rate of spread, and this is a challenge for us to investigate this. Extreme fire behavior is not synonymous of very large fires, because extreme fire behavior may happen even in relatively small fires, but of course it's more likely to occur in large fires. Accidents in large fires involve usually extreme fire behavior processes, some of which are not yet well studied. With scientific research, we have to improve our knowledge on these processes, and that's our purpose. Okay, I stay here and I'm at your disposal. Shall I stop sharing?
Yes, thank you. Professor Viegas, thank you so much for this lecture and putting science behind all these examples that help understand what have happened and how to better understand extreme wildfires. Appreciate very much both presentations. First, Edwin, putting in context of the Netherlands perspective, what is need from science, this needs for collaborations with science and internationally, and understand of some processes. And then Professor Viegas providing some research answers, hopefully to some of the questions that Edwin had in the first place, but also to many other phenomena that it's seen in the fires around the world. Thanks so much, both. The idea now was to have some Q&A. I would first like to give the floor, Edwin, if you have any specific questions that you would like to ask Professor Domingos, but also everyone else in the audience. If you want to ask some questions to the speakers or throw any comment in the debate, please either raise your hand to speak and participate, or post your questions in the chat. Okay, so Edwin, for the time being, is there any point that you would like to raise to Professor Domingos as a starting question for this Q&A?
No, not specifically. I think it's a great presentation, which shows how scientific knowledge is used for operational firefighter safety, for example. So I saw some questions already in the chat, and I think this is the kind of questions we are going to discuss about in this Q&A. So the question Hector Alvaro is asking to me is about how do you convey the information in the Netherlands to the frontline firefighters in a way that they can easily understand it. That's kind of the same question I can ask to Professor Viegas. So maybe he can answer first, and then I can do the Dutch part for them.
Thank you, Edwin. Since the beginning of our research, we tried to convey our knowledge to the firefighters. And I can tell you that at least since 2004, so 20 years ago, we have a protocol with the National Fire Brigade School, under which we give training to the firefighters. We give them lectures on the extreme fire behavior and on case studies of past accidents. And then the firefighters come to the laboratory and they show them experiments on this behavior in slopes, in canyons, fire worlds, and other types of situations for them to understand the dynamic aspect of fire behavior. That is our main message for them to know that what the fire is doing now may be very different from what it will do in the next 5-10 minutes. And we are proud that more than 5,000 of the Portuguese firefighters have come across our laboratory. And they are, let's say, they are exposed to this type of fire behavior, and they understand. For example, if they see the experiment that I showed you of the accident of Armamar, they are very impressed to see that the wind is blowing in one direction, and then when the fire comes to the entrance of the canyon, it spreads at 90 degrees with a very fast spread, and you cannot be there. So this is very important, what you say, and we realize that, and we try to convey our knowledge to not only to the firefighters, as you said, also to the citizens, to mayors, and everyone that has to do with the fires. We explain them what happens, what can happen in a fire.
Thank you, Professor. And do you also include operational firefighters in your research? So you are teaching them the lessons learned. You're teaching them what you found in your scientific research, but are you also including them in front of a research to know what they need to know, for example? And of course, you know a lot about what they need to know, but
that's right. I can tell you that 40 years ago, when I started this, they did not understand what we were doing, and it was not easy to have a dialogue. But let's say, when going to the field, going to the fires, talking with them, and when analyzing large fires, as we did in the past, we had, of course, to interview lots of firefighters, fire commanders, and to get their perception and to exchange ideas with them. And so it was easy to start this dialogue. And when we started to understand this type of fire behavior that is changes very rapidly, and could be a surprise for them, but cannot longer be a surprise because we tell them this is what will happen. They understand that what we are doing is relevant for their life, and so they accept very much what we are studying and what we are teaching them. So we have a very good dialogue with the firefighters, not only from Portugal. We are also receive, as you mentioned, this exchange from northern countries. We receive in our lab groups of firefighters from the Netherlands, from Germany, from Switzerland, from Sweden. Different guys come here to see what we are doing.
Great.
And Edwin, from the perspective in the Netherlands, to complement to what Hector was asking, what is being done? How do you see it?
Now, what's very interesting is that our knowledge is way less than in Portugal, for example. So we haven't done a lot of research ourselves in this topic. So we are doing basically two things. First of all, we send our wildfire specialists to Southern Europe to train actually with the firefighters over there, and because there's a lot of knowledge, they can use that knowledge to also implement this in the Netherlands. And the second thing we are doing is trying to make them aware of that you can predict in certain ways which fire behavior you can expect. And that doesn't mean necessarily that you know how to fight a fire, but you can at least expect some kind of fire behavior. And that's why we started this year with a group of fire analysts. And also for this fire analysts, we are using the knowledge from Southern Europe and from the AFON network to tell our operational firefighters, okay, we can be better prepared for the situation that is unfolding. So by now we make, if it's dry, last year it was very wet in the Netherlands, but if it's dry, we make a document every week, or if it's necessary, more times in a week, with a prediction of the potential fire behavior. And we give this information to all of our operational firefighters, and we say, okay, be aware, this can happen. Doesn't mean it will happen, but it can happen. But I think we need at least 10 years to bring in a lot of knowledge in our operational firefighting, because this year we started a project where we developed training materials for the Netherlands. Like I said, for a very long time, we just went to the fire, we went to the head of the fire, we killed the fire, and then we got back to the fire stations, and that doesn't work anymore in some kinds of situations. So we started a very large project this year for all training materials. We collected all kinds of training documents from America, from Southern Europe, from the Netherlands itself, and with a group of firefighters, we went through all those documents and said, this is relevant, this is relevant, this is not relevant, or this is just relevant for the specialists, for the higher trained officials, etc. So we're rubricating the topics, and we make sure that every firefighter in the Netherlands has the same information based on those scientific principles. But before everybody knows that, we for sure we need 5 to 10 years to make that part of the organization. So yeah, we are facing a very large challenge to bring this knowledge to our firefighters. And on the other hand, we try to put our specialists in the researches we are doing in international researches and collaborations to give their ideas of what we need to find out, what we need to know to be better prepared for wildfires. Yeah.
If I can comment on what you said, Edwin, I think that you should aim for less than 5 or 10 years. I think that sooner than that, you should get that knowledge, because things are happening very fast.
Yeah, we aim for that, but like that's a very small insight in how the Dutch fire service work with a lot of volunteers. We have about 2 to 4 hours.
I realize that what I'm speaking here is knowledge that is incorporated by some groups of firefighters, but not all of them. And even some experts, they don't know all this, and we are trying, let's say, to disseminate this knowledge, especially this latest knowledge that I presented about the fire acceleration and deceleration. It's a paper that was submitted for publication. It's not yet published, but I think it's important to share and to disseminate this knowledge and to get, let's say, joint practice on it as well. We need data to improve it and to validate it. But we know that this will be necessary in a quick time. Let me tell you one comment about, you mentioned about wind fires and topography fires, or convective fires. This, in my opinion, is not very correct concept, because you noticed what the images I showed, the fire accelerates and it creates a plume. That can happen, and people call that a topography fire, a convective fire. But that can happen even in flat ground, as you saw in those images. So in Netherlands, you can also have that type of behavior. It's not a topography fire, because that is something that people say erroneously, because wind and topography is always there. The fact that the fire has, let's say, a process, a dynamic process that has that acceleration, it goes under different stages. That acceleration phase looks as a wind-dominated fire, but when it stops, it looks like a convective-dominated fire. But it's the same fire. It's the boundary conditions are the same. The fire is creating its environment. It modifies, but the fire is the same. And you will have that also in the Netherlands sooner or later.
We've seen already some convective fire behavior. We have a few examples, at least 3 in the past 10 years, that we had convective fire behavior. So yeah, we are seeing this. The challenge is I totally agree that we, in an ideal situation, we have this knowledge to the firefighters within 5 years, but we have about 2 to 4 hours of training per year for wildfires in the Netherlands for the firefighters. So that's a lot less, I guess, than in Portugal or in Spain. So now we are trying to train our specialists. We have wildfire technical advisors, fire analysts, hand crews, a helicopter team. So we are trying to train the specialists in this advanced knowledge, and they need to disseminate it to the other operational firefighters. That's for now the best way to do it. But to train all the firefighters, yeah, I think we need the time, and that's maybe we don't have it, but we need it.
Thank you. There are also a couple of interesting questions in the chat. One is from Nikos. Is there a process in Portugal on supporting field commanders during an incident, as for short-time forecasted behavior of fire fronts?
Well, there is in Portugal, there is a service at the Civil Protection Agency, where there is a specialized group that receives information from the field and they anticipate the behavior of the fire. Actually, Fabio Silva, who is with us, was also part of that group, and they provide guidance and assistance on the expected fire behavior. But to my knowledge, I think that this sudden variation of the fire spread are not yet incorporated in those models. We are working to put them in the form of codes that can be used depending on the different boundary conditions, what you can expect that the fire will do here and there in the next few couple of hours. And this is, as we were saying, a knowledge process that we need to have more interaction with that.
Mm-hmm. Fabio, since you are here as well, would you like to make any comment about what Professor is commenting?
Yes, I can add something. So yeah, we have unity into the national command of the National Authority of Emergency and Civil Protection in Portugal. So during the emergency, we already have the one format, one page that we can send to the incident commander. So which has the information about the prediction of the meteorology conditions the next hours. So the prediction of the fire behavior to next hours and tactical proposals. The minimal is 3, the maximal is 5 priorities for this wildfire, and some tactical proposals. It's general proposals, of course, and also we add something about security, so some dangers. Of course, this kind of analysis is not depend of the fire simulation. Fire simulation is one more tool that we use, and of course, the most important thing is the knowledge of the fire analyst. So I think the most important concepts, and the presentation of the professor was amazing because we put the focus in 2 different important descriptors. One is rate of spread, another one is about fire line intensity. So I think it's crucial the operational people understand very well these 2 concepts, and maybe the other concept is about the rate of growth, the wildfire. So, but it's very important to understand the variables that depends the rate of spread, and after that understand very well what we have sometimes a lot fire intensity or not. I completely agree with the professor when I think it's very important we understand and predict when we will have deceleration and deceleration, because in this way we can predict very well when we will have the complex, I will not say the extreme, but the complex fire behavior. But and we can predict this moment, but the most important thing, we can predict the fire opportunity, the window opportunity in this case. So the most important thing when we do this kind of analysis is identify the worst moment and try to put the information about the window opportunity and try to create some tactical proposals. And of course, the main objective goals for this kind of wildfire.
Thanks, Fabio. There's also another question on the chat for Professor Villegas. How we can relate the rate of spread and the fire radiative power?
Thank you for the question. I think that the rate of spread that I was mentioning is about the head fire, and the radiative power it comes from the entire area that is burning. So there may be some delay or discrepancy because the whole fire is releasing heat power, but the head fire may be releasing more or less. Of course, if the fire is accelerating, the intensity will be higher and the heat power will be higher. So comparing the differences between the images, you can estimate the rate of spread, and you comparing the differences in the radiated power, you can also see what comes from the head fire, which is the most relevant part of the fire.
I think it's a crucial point because the people relate a lot the intensity with the radiative power. Yes. So I think it's very important to understand. So we have a lot limited. It's not the right word, but we have some limitations. For example, in Pedrógão Grande, we don't have any information about fire radiative power because when we have cloud covers, we have some difficulty to understand this kind of information. So I think it's very important information about fire radiative power. It's good, but we need to understand very well that in Portugal we have a problem about resolution, but also this information is about all this area. When we have thousands of hectares, we don't know too much about this kind of information. When we have one kind of the species, because for example eucalyptus, we have a different energy if we compare with other shrubs or other kind of the other species. So again, I think it's crucial, and I think we have some difficulty in this part. I think it's crucial we understand two different concepts. Rate of spread and fire line intensity is crucial. So fire line intensity defined by Byron, it's very old. So we have a lot of information about this kind of concept. So now we are trying, and this forum is a very good example. We are trying to translate this complex information in operational language, but we need that everyone put the focus in the most important concepts. So because in the last few years we spoke about a lot about pyroconvection, but we don't know nothing about soils, vegetation, how dry is this vegetation, and the most important concepts, as I said.
Thank you. To follow up with some questions for Professor Villegas, you mentioned there are some limitations on the models from going from field experiments, lab experiments to large wildfires. Is there any effort or action to collect data jointly with practitioners in the ground during large fires that can help validate the models you have presented?
Thank you. My team is doing work at the laboratory where all the parameters can be measured very detailed and also in controlled conditions. So this is very important to understand the basics and the physics. We do also field experiments where the processes are not so controlled. We depend much on the other conditions, and we observe and analyze real fires. And nowadays there is much more facility to get data from the fires, because with remote sensing we have very detailed images, both in time and in space, with a great, let's say, resolution that we can analyze. So we are gathering all this information. One thing that is very important that we found is that the same process occur in the whole spectrum of conditions. We, from the laboratory to the field, we observe the same type of behavior. Only the scales and the amplitudes, for example, of the oscillations on the errors are not the same. They are much bigger in the larger scale. So it's important to look at the whole spectrum. But it is important to know that when we study the process at the laboratory, we can understand, we can get insight to the issues that occur in the field scale. As I showed you in the examples of the canyon fires, of the junction fires that we do at experiments at the laboratory, we observe the same type of behavior as in large fires. And we are working very much with the different agencies, not only in Portugal, but also internationally, to get data to improve the models regarding this limitation that I mentioned.
So perhaps this is also a call for everyone attending the webinar today. If there's some interest in collaboration in helping and support collect data, I'm sure Domingos would be very happy for that.
Thank you. Thank you.
I see there are no more questions in the chat for now. Actually, yeah, there is one. Last one for Edwin.
Just now.
Just now. Very good, Nikos. Is there an established technical analysis of wildfire incidents in the Netherlands? Given the individualities of the Netherlands landscapes, it is crucial to create a history inventory, since Mediterranean countries' input may be even misleading. What do you think about that?
Yeah, that's a very good question, and we are working on it. We have a team of wildfire investigators that's already active since I guess 2014 or something like that. So for the larger fires, we do a technical analysis of the fire, and that's based on two things: the cause of the fire and the way that the fire spread, to learn from it. So we did that for all the larger fires in the past 10 to 15 years, but we want and we need to do it for much more fires, also for the smaller fires, because it's very interesting to know why a fire keeps small. So we can do a lot of research to find out why a fire grew big and what were the drivers for a fire to get big. But maybe it's more interesting to know why fires will stay small, because then we know how to how to extinguish those fires effectively. So in the vision I was talking about, we stated that we want at least 60% of the fires investigated by 2028, 2030, in that kind of period. So we need to train more people, more investigators to actually do those technical analysis of the fires. And we need to develop a system like I saw in Portugal, and I know a lot of other countries do have it, with the parameters on it and the historical information of fires and type of fire behavior, etc. So we need to develop it. We are working on it right now, but it needs a lot of improvement. So yeah, I think that's the basis for our country and maybe for all Northern European countries to improve your firefighting and to improve your knowledge about wildfires, that you need the data at first to know what is happening, to know if you see changing fire behavior, to know if you see larger fires or smaller fires, or more fires or less fires. So data is the first thing to know what is actually happening in the country. Yeah.
Thank you, Edwin. Also, perhaps it could be interesting to mention, perhaps is Georgios, you want to intervene here, but NERO is also collecting information about extreme wildfire events across Europe and the world, and it's looking to analyze fire behavior as well. I'm not sure if there's more information about that already available on the website, but there are certainly some actions ongoing, and you can find more information soon in our channels if you want to contribute or you want to follow what is going on. Then finally, I have a very, very last question for Edwin. Since you were involved in the network activities and the exchanges, can you explain everybody what is that a little bit? So if somebody wants to get involved, understand what are the possibilities?
Yeah, there will be a little bit of a sales talk because I really, really liked it. So I got the opportunity to join the special forces, the how to read that, Fabio knows, but the National Civil Protection Center in Portugal for a week to join the wildfire analysts that are sitting there. Like I said, we are starting a wildfire analyst team in the Netherlands too. So our main target was to get the knowledge and the way of working of those fire analysts in Portugal to see if we can adapt this also in the Netherlands. And I joined there for a week. We didn't have very large fires, but we had some interesting fires, and I got the opportunity to join the analysts. And what they do, they make every day a strategical analysis. That was in one of my my sheets in the presentation. That's the prediction for the next 3 days of what the weather is doing in a more general way. We do have kind of the same system in the Netherlands, and they are doing real-time analysis during a fire. So what I saw, for example, is if you have good images and they have fire towers or they have camera towers where you can directly see smoke columns, etc., then you get a very good view in the first minutes of a fire if a fire has potential or hasn't potential. And I saw the operational system where all information is combined. So information about vegetation, information about pictures, etc., resources, where are the resources positioned and what are they doing. So all those things I saw, and I made a whole report of it for our Netherlands Fire Service and for our institute where I'm working for, to say these are kind of easy things. Not to say that the work that they are doing is easy, but the systematical analysis and the way of working in Portugal, we can directly implement this in the Netherlands and in Germany and in the UK and in Sweden if you want to, because it's based on common knowledge. And if you learn from this kind of experiences, and we also have a very good collaboration with the Catalan Fire Service, with the Graaf, we try to implement a lot of those things that they are doing already there in our Netherlands Fire Service, because those knowledge is necessary for what we're doing. So I can recommend everybody. The good part is also it gets paid fully by the European Commission or by the NERO project, but by the European Commission. So you get all your all the money you need to go actually to Portugal or to another opportunity that will be there. Will be funded, and it's a unique way to learn actually from the specialists in those countries. So especially for all Northern European colleagues in this meeting, please go there and take this opportunity to learn from our colleagues. Yeah.
Thank you very much, Edwin. Yeah, just check the website, NERO website, for opportunities for these short-term stays. The only requirement is being a NERO member, and this is very easily to do. Anyway, thank you very much, Edwin and Professor Domingos, for these amazing presentations and webinar on your insights and perspectives. I think we all had a lot of fun and we learned during the webinar. So appreciate very much your contributions. Also, thank you everybody who's joined today. Hope it has been a useful and interesting morning. For the ones that want to see the webinar afterwards, this will be recorded and available on the NERO website. So please check there. And also the future webinars will be also announced on the website and through the NERO channel. So please stay up to date for the next webinars that we will propose. Thank you very much, everyone, and have a great week.
Thank you.
Bye all.
Bye, everyone. Have a good day.
Bye, everyone.